how it starts. We go back to your house.
So this equation, having a second order ODE, which is a linear homogeneous equation, looks like this. So y double prime plus p times y prime plus q times y is equal to 0. So let's look at this. The 0 means that our forcing term is equal to 0, which gives us the homogeneous part, right, of our equation. And then our p and q in this case are constants, okay? So constants meaning just numbers like 2 or 3 or 4 or something like that, okay? So p and q are constants, and everything else just appears as such, the y double prime, the y prime, and the y. Okay, so here's the key idea to solving this kind of equation. So here we have it. Let's look at, so basically we have that y of t, which is equal to c, some constant, times e to the negative pt, is a solution to, and this is a completely different equation, okay? So y prime plus py is equal to 0. Okay, but it looks kind of similar, right? This is a first order linear homogeneous equation, okay? So what we're going to do is build off of this and say that, well, based off of this solution here, we're going to look for a solution to our second order linear homogeneous equation that is of the following form of y of t is equal to some kind of c, some constant, times e to the lambda t. And whatever this lambda is, we're going to find that out, okay? So this is the kind of solution that we're looking for. All right, so here is the process of finding a solution. Here's the process. Okay, so we have our original equation here that looks like such. Okay, and what we're going to do is actually there's a corresponding what's called characteristic equation for this ODE. Okay, so the characteristic equation looks like this: lambda squared plus p lambda plus q is equal to 0. Okay, so it's kind of like not a direct translation, but it does look pretty similar, okay? There is a derivation of this in your book to see how we get the characteristic equation, so you're welcome to look at that, but we're just going to go from here, okay? So this thing here is called the characteristic equation of that ODE, of the above ODE, okay? So this one here is our ODE. Okay, so then from here, we're just going to find the roots to this, characteristic polynomial. That's another term. Characteristic polynomial. So the polynomial part just means everything on the left-hand side of that equation, okay? So we're going to find the roots, and then once we do, then we do so by using the quadratic equation. So this is lambda is equal to negative b, which is negative p, plus or minus the square root of p squared minus 4ac, which is 4 times a q in this case, and then all over 2. Okay, so this is how we find our lambda. You just plug it into the quadratic formula. Okay, and then 3 cases arise. Okay, so then I'll show you on the next slide what cases could arise. So once we get our lambda, which again I'll write it here, so negative p plus or minus square root of p squared minus 4q, and this is all over 2. So then 3 cases could arise. Then we have case 1, we have that p squared minus 4q, so this thing is called the discriminant, right? So everything inside the square root, let's say it is positive, okay? So then we can take the square root of a positive number, so we're fine, and we'll get 2 solutions. Then we get 2 distinct, they're called, 2 distinct, meaning different, real roots, and real meaning in the real numbers, okay, that actually exists. And then our second option, or second case that could happen, is p squared minus 4q is less than 0, which means we have a negative number inside this square root sign, which will actually give us 2 distinct again, different, complex roots in this case. So complex meaning that it involves imaginary numbers. Okay, so we're gonna have some kind of i's floating around because we're taking the square root of a negative number. And the third case is when p squared minus 4q is exactly equal to 0. Okay, and then that would get rid of this whole plus minus sign because we'd be having plus minus 0, which doesn't really affect anything. So then we would just get the one root would be actually lambda is equal to negative p over 2. That would be our root. So anyways, the important part is that we have one repeated real root. Okay? So building off of this, let's explore each of these cases in detail.
I could be with my friends tonight.